Hello students, welcome back to your astronomy lab. This lab is going to be about the circumpolar stars. So you're going to learn about the circumpolar stars, what they are, and some uses for them for navigation and timekeeping. So you're going to be following in the footsteps of ancient astronomers and travelers, and we'll be using the stars as a guide map for location and time calculations. So specifically what we're going to be looking for is the latitude of the observer, the length of the solar day, and the length of the sidereal day. So before we get into what we need for the lab itself, one thing for background is the celestial sphere. The celestial sphere was an idea, an ancient idea of how the universe actually worked. So the idea was that the Earth existed at the center of a giant sphere. So as this idea evolved, the Earth was a small sphere in a much larger sphere, and that larger sphere had all of these stars on it. So the sun and the planets and comets and other things that would move around the sky weren't considered stars that were fixed on the celestial sphere, but pretty much everything else in the sky was. So you can imagine that the Earth exists in the center, and the celestial sphere is just a much larger sphere out from that with stars painted on the walls. Now we know that the Earth rotates, but the idea was that the celestial sphere would rotate, and even though this idea has been proven to not exist, it's still a useful way to look at the sky. It can explain many of the things we'll be talking about today. So we're going to be using this idea of the celestial sphere. So the Earth exists in the center, and the Earth rotates on its pole. So imagine that there is a pole going through the Earth, and that pole is being spun like a top. This means that if you were to stand on the North Pole and look directly upwards, as the Earth spins, you would always be looking at the same spot, and the same thing would happen at the South Pole. We're lucky in the northern hemisphere because our north celestial pole has a relatively bright star that exists at that point. That's known as the North Star. So if you stand on the North Pole and look directly upwards, you would always be looking at the North Star, looking at Polaris. If you stood somewhere other than the North Pole and looked up, you would be looking at some point on the celestial sphere. And then as the Earth rotated, that point would change. So you'd be looking at different stars on the celestial sphere. If you're at some point other than the North Pole and you look to the North Star, it would be some angle above the horizon. So we already learned about how angles are used to measure lengths in the sky. If you continued moving away from the North Pole, eventually you would be at the equator. If you look straight up, you would be looking at the celestial equator, which is not visible in the sky, so it would just look like more stars. And as the Earth rotated, you would see that those stars would change. If you looked for the North Celestial Pole, or the North Star, from the equator, you would see that it was right on the horizon, and the same thing with the South Celestial Pole. These poles would be right on the horizon because you are halfway in between. Imagining that the Earth is locally flat, so since the Earth is very big, we don't really notice its curvature. If you were standing right here and the Earth were locally flat, you would just see these two poles on the horizon, and that would make sense because the Earth is very big. And then if you continued southwards, the North Celestial Pole would disappear below the horizon, and the South Celestial Pole would begin to rise in your sky. And eventually, if you reach the South Pole, the South Celestial Pole would be directly overhead, and as the Earth spun, you would always be looking at the same spot. So what this means is there is a relation between where you are on the Earth and where your celestial pole appears. So we will stick to the North Celestial Pole just because it's the one most of us will be more familiar with. But again, if you're at the North Pole, it will be directly above you. It will be 90 degrees above the horizon. If you're at the equator, it will be at 0 degrees above the horizon, right on the horizon. So in between, somehow this must go from 90 degrees to 0 degrees above the horizon. And it does that very smoothly, and that allows us to mathematically say that your latitude or your distance from the equator will be the same as where your north celestial pole is above the horizon. So if you were 1 degree latitude, just right above the equator, your north celestial pole would appear at 1 degree. In North Dakota, I believe we're around 45 or 50, somewhere in there. So our north celestial pole appears about halfway between the horizon and directly above, or halfway between the horizon and your zenith. And then as you go closer to the North Pole, your North Star will be higher and higher in your sky. So that is some background just to the celestial sphere and how we can use it to relate where our North Celestial Pole is to our latitude on the Earth. And we'll be using that in today's lab. So like I mentioned, the latitude can be determined based on the position of the pole with respect to the viewer. If you're closer to a pole, you will get a larger angle, and if you're at the equator, you'll get a smaller angle. You can find your stellar pole by looking at the stars that rise and set near the celestial pole, and that is what we'll be getting into for most of today's lab. So those are known as your circumpolar stars. So a good way to look at them is to have some sort of representation of the night sky, and in your lab you will have something very similar to this. This is the northern sky for somewhere near Fargo or near Moorhead on a night like tonight. So here's the horizon, here's the sky. I believe around here is looking directly upwards. So as we go from the daytime through sunset, the stars come out, we see that as the Earth rotates, certain stars will set. So we can see Arcturus over here should set, and then certain stars and planets will rise. So the Pleiades and other stars will begin to rise as the night goes on. We also see that as the sky rotates, one star does not appear to move, and that is our North Star. So that is Polaris. And other stars do move, but they will never set, and those are our circumpolar stars. So if we draw a line down from Polaris to the horizon, that will give us an angle, and then that angle distant from Polaris will be the region where our circumpolar stars exist. So they will never set for this area of the world. And there are some well-known constellations in that circumpolar region that we can use for useful purposes. So just look as the stars go around, Polaris stays in its same spot, and the circumpolar stars do not rise or set. So one thing I want to point your attention to is that the Big Dipper is in the circumpolar region, and that's very useful because Polaris isn't a super bright star. It's just bright enough for pretty much everybody to see it, but it doesn't stand out for being super bright. So using the Big Dipper, which is usually quite easy to find the two stars furthest from the handle, and then draw a line upwards, draw a line in the direction that liquid would need to go into the dipper for it to be useful. So the two pointer stars extend upwards, and the length you need to extend is about 4 times the length between them. They point right at the North Star. And that is how you can find the North Star. So if you're in a night sky and you can at least find the Big Dipper, you can use that to find the North Star. And then if you know the North Star and you have something that can measure an angle, you now know your latitude on the Earth. So that is one of the things you'll be doing in today's lab. The next thing you'll be looking for is the solar day. This is what most of us think of as the day. It's the time between a solar event to the next time that repeats. So from dawn till the next dawn, or from sunset to the next sunset, or even noon, or measuring some angle of the sun being above the horizon. The simplest way to measure this is just to time from one solar event to when that repeats. So from dawn one day to dawn the next day. If you measure that, you should get a good idea of what the solar day is. However, if you desire to get a more accurate measure of this time, it can often be better to measure several of these events and then divide out by how many times the event actually occurred. So getting an average time for this event to occur. So your length of your solar day would be the time for a solar event to repeat n number of times divided by that number. So if you measure a week's worth of dawn events, so from dawn on Sunday to dawn the following Sunday, measure that total time, and then divide by 7 times that event happened, you should get a better measurement for the length of the solar day. And you could do this as long as you wanted. You could do it for a year, you could do it for 1,000 years if you want your measurements to be better. However, the solar day is not always the same. We know that in winter we have much shorter days, and in summer we have much longer days, so there is some change that happens. So be aware of that. Using more days will not always give you a more accurate measurement for your solar day. And then your sidereal day. The sidereal day is the time it takes for the Earth to make one full rotation, or relating back to the celestial sphere, the time it takes for one star to make a full circle about the pole, or a star to return to the same spot in the sky. And just to point out, the sun does not count as one of these stars. In order to calculate this, it's best to base your calculations on a partial arc from a star taken from a long exposure lens, and this is because stars are not always visible to make a full rotation due to the sunlight blocking out our view of these stars. So if you are in an area like the North Pole, the Arctic region where it can be dark, you can make this measurement by looking specifically at a star making a full circle, but for the rest of us we have to extrapolate from a partial arc. So the time for a total rotation is the time to complete a partial arc times 360 degrees divided by the angle of a partial arc. And what will that mean for you in the lab today? Basically, you will be looking at a specific star. You won't have a crosshair like I have here, but you will have grid lines which make it easier. Here we have our North Star Polaris, and right at this time here, Alkaid is about even with that North Star. So if we had a clock, this would be at about 9 o'clock. Moving the sky a partial rotation, so I've moved it about a quarter of the way through its full rotation, so it's moved from 9 o'clock to 6 o'clock. Alkaid has made a quarter of a rotation, and if I continued this on, we would see that even through the daytime, with this software, we can track where the star is. The start of the next day, the star will start in the same spot, and eventually we will see the star return to the spot we began measuring. So with software, we can do this. In real life, this is not always so easy. So what we would measure is the time it takes Alkaid to move from here, 9 o'clock, to 6 o'clock. And you'll be doing this in the course of today's lab. What angle is that? Well, it's a 90-degree rotation. If we moved all the way over here, it'd be a 180-degree rotation, and then all the way back to its beginning spot is a 360-degree rotation. But since we have the 90-degree rotation, this amount of time, using that to extrapolate how long it would take to make a full rotation. And really, any star could be used for this. The circumpolar stars will be easy in the lab you're doing today. But if you can watch long enough, basically just looking for a star to return to its same spot. And then we'll be doing the same thing with the solar day. So right at where sunrise happens, it will just show up as your screen, the star is disappearing on your screen, but you can measure the time of sunrise and then go through a whole day, and then measure the following sunrise. And if you do this a few times, you'll get a pretty accurate measurement of how long the solar day is. So I believe that's all you need for today's lab, plus a few other things that I think would be helpful just to know in general. If you have any questions, ask your TA, and good luck and have fun.